This is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we are discussing solid mechanics and material subject. So in this subject, already we have discussed some topics, and in previous session we have discussed about bending stresses in beams. So in this, what do you mean by pure bending, and what is the theory of bending, and then how to derive the bending stress equation for a beam whenever the beam is subjected to movement or subjected to different loads. So in this session, in today's session, so we will discuss about the position of neutral axis and how to calculate the moment of inertia. So we will discuss these two topics in bending stresses in beams topic, beams 2 topic. Clear? First of all, we should know about outcome of this topic. So we analyze the theory of simple bending, illustrating the distribution of bending stresses across the section beams under loading. So after completion of this module, the student should be able to analyze the theory of simple bending. They can derive, they can analyze so of this theory of simple bending, and also for illustrating the different distribution of bending stresses for different beams under different loads. So that is the main outcome of this topic. So before going to enter this position of neutral axis and moment of inertia topics, so we should know about the bending stresses in beams introduction part. Already we have seen in the previous session. So once again recall the bending stresses equation and beams. So the bending moments and the shearing forces are set up at all sections of a beam when it is loaded with some external loads. As a matter of fact, the bending moment at a section tends to bend or deflect the beam, and the internal stresses resist its bending. So the process of bending stops when every cross section set up full resistance to the bending moment. So in this, the resistance offered by the internal stresses to the bending is called bending stress. So the relevant theory is called the theory of simple bending. So the resistance offered by the internal stresses to the bending whenever the beam is subjected to different loading. So note down, the bending stress is the combined effect of both the tensile and compressive stresses. So I will show you in a diagram these two stresses. See, so whenever the beam is subjected to the movements, so before deformation the beam is like this, uniform. So after bending, so after deformation, it means after subjected to some loading, the vertical lines remain straight, and these vertical lines there is no change, but only change in horizontal lines. These horizontal lines become curved. So it means so the beam undergone some deformation. So these in this beam, these top layers are subjected to compression and bottom layers are subjected to tension. It means elongate. The curvature radius will be increased at the bottom portion. There is no change at middle. That is called as neutral axis. So we will discuss later. And top portion is undergone compression. See, so see in this diagram, the beam, the bending is the beam bending is like this. So whenever subjected to moment and point load and UDL. So the compression, the top layer undergone compression and bottom layer tension. See, in cantilever beam case, so the beam is the bending like this. In this, the top portion is tension, tensile nature, and the bottom one is compression nature. Whenever the load is acting at this free end. So now, so we have derived the bending stress equation in the previous session, and also we have recalled about the bending stresses introduction part. Now we will see position of neutral axis. So what is this neutral axis? You know, in this beam, the central axis, central line is called as, this one is neutral axis or neutral layer. So there is no change in length or curvature radius whenever subjected to load. This layer is called as neutral axis or neutral layer. So the line of intersection of the neutral layer with any cross section of a beam is known as neutral axis of that section. So we have seen that one side of the neutral axis there are compressive stresses, whereas other there are tensile stresses. At the neutral axis there is no stress of any kind. See, in this previous beam, so in the one side the neutral axis, one side tension and another side compression. But at this neutral axis there is no stress. Clear? So we have seen one side of the neutral axis there are compressive stress. Other side tensile stress. So it means that in neutral axis there is no stress of any kind. So take this section example. Consider a section of the beam as shown in figure. Let neutral axis be the neutral axis of the section. So let NA be the neutral axis of the section, NA. So this is a beam and then the elemental cross sectional is PQ. So NA is neutral axis. So consider a small layer PQ of the beam section at a distance y from the neutral axis as shown in figure. So the distance of this beam section considered as a y as shown in figure. The y is distance of beam cross section from its axis. Which axis? That axis is called neutral axis. So now let delta A, the area of the layer PQ. So this layer area. We know that the intensity of stress at a distance y is equal to y into E by R. So, you know the bending stress equation already we have derived in a previous session. So sigma by the bending stress by y is equal to E by R. Clear? So here E is the Young's modulus and R is the radius of curvature. So y already we have assumed that is the distance from distance of the beam cross section from its neutral axis. Now the force on the layer is stress on layer multiplied with the area of the layer. So the stress on layer is here bending stress, that is sigma, multiplied with area of layer delta A. So now substitute the sigma is equal to y into E by R into delta A. So the total force on the beam section is obtained by integrating the above equation. Now we have taken only force on the layer, one layer. So integrate this equation, we will get a total force on the beam section. So the total force on the beam section is integrate E by R into Y into delta A. So this is sigma, the force, the total force, the force on the layer, that is intensity of the stress at E sigma multiplied with delta A. So this is total force. So but the pure bending, there is no force on the section of the beam, or force is zero. In pure bending theory, we have learned there is no force on the section of the beam. So that here take common E by R and integrate y into take the position of neutral axis. So we have seen in this slide. So we have taken delta A, small elemental area, and then the intensity of the stress at a distance y we have taken, and now the force on the layer, the stress on layer multiplied with area of layer. So that is we have taken sigma into delta A. So now calculate the total force on the beam section. So here the integrate, first we have taken small elemental area, that is P into Q. The y also we have shown here from its neutral axis y. So E by R take outside and y into dA. But the pure bending, there is no force. So here you will consider these two, the E and E. So for this diagram, in this, the E and R is, you can take as constants. E and R are constants. So it means here there is no effect on this total force on the beam section. So that it means there is no change. That is the R radius also, there is no difference in their radius. So take example this one. In this, the top layer undergone compression and the bottom layer tension. The between neutral axis is there. So in this, in neutral axis, there is no change in the radius. So the above is compression and tension. So that is called a neutral axis. So at this stage, the E and R is constant. So that's why you can take this E by R outside and then integrate. You will get the total force on the beam section. You know, the y square by 2 into the delta A. So delta A is here, you can take the area of the layer PQ. So like this, you can fix the position of the neutral axis. Now take example here, the cross section. The cross section is rectangle. So from this section, so how do you take the neutral axis? So from its example, this is neutral axis and take the y. So the half of this total distance totally is b. So the neutral axis distance is b by 2. Clear? So similarly, for cross sectional circular cross section, this is y. This r by 2. So this is r and then r by 2, y is equal to. So always the position of neutral axis at its middle of the beam. So already has shown we have discussed in beams at bending beams diagram. So in this, see the neutral axis always its center of its beam. So while calculating bending stress or bending stress equation, so this neutral axis distance plays a very important role. So that's why the line of intersection of the neutral layer with any transverse cross section of a beam is known as neutral axis of that section. So take here, see the here bending moment equation. So what is the bending equation? So already we have derived in a previous session. E by or sigma by y is equal to E by R. Clear? So in this, and then you can write in elaborately this one m by I is equal to sigma by y is equal to E by R. So m is your bending moment, I is the moment of inertia. So I will discuss in a next session moment of inertia. And then bending stress, you know bending stress, and then y is the, now we have discussed the position of neutral axis. For every beam, first you have to fix this position and then take the Young's modulus, and R is the radius of curvature. Clear? So total, so in this these two are constant, you will get total force of the force on the layer. Whenever you integrate this equation, you will get. So apply this equation. So that's why while calculating bending stresses, the position of neutral axis is very, very important. So fewer bending, already you know the no force on the section of the beam. So for this PPT, I have taken references S. Ramamurtham, The Strength of Materials. The title of the book is, publishers is Dhanpati Roy. And R.K. Rajput, Strength of Materials. The title of the book is, and publishers are Yashwant and Co. And R.K. Bansal, the title of the book is Textbook of Strength of Materials. Publishers are Lakshmi Publications. And one more book is R.S. Kurmi and Gupta, The Strength of Material title, and then publishers are Yashwant and Co. So these are the references I have taken for this PPT. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.